Hey, hello, how you doing? How you doing?
Doing good. How about you?
Uh, Feeling late. Shot a Zoom class later than used to be there. Yeah, that's what happened to me just now. Okay, so maybe I should start by we'll see. Okay, share. Excellent. So you should be seeing now a screen, the regular thing that we do in Stat 313. On a note, goddamn, maybe verify we're on the same page with regard to the exam. Got sort of a gnarly lag in my internet as for that. In fact, this is pretty bad. Okay, so finally, what I'm seeing is, yeah, there's this exam coming up that I guess we were officially starting it tomorrow. So tomorrow, right after class, the exam will be live. Okay. We have one last topic for the exam, and that's sort of today. But really, one, we've done all these things before in chapter 8 and 9 in some fashion. And two, the exam is emphasizing content through the partial F test, Monday's class. So chapters basically 4, 5, 6, 7, and then the partial F test. That's the emphasis on our exam. Um, but the things that we're going to do today, yeah, if you understand the material, sort of work through the lab, you're going to be better prepped for the exam. And like always, tomorrow, before the exam is released to you, we're going to have sort of time to go over any questions you have from the sample exams or anything else. And then I guess it's just 1, 2, 3 class sessions that are formal, then a review section, and then the final exam, which is scheduled for in person on Thursday, the 23rd. Do any of you have questions about anything at all? I guess with regard to sort of schedules or stuff like that, non-subject matter questions, administrative questions, perhaps. Okay, so where we're at then is we did talk about the partial F test yesterday in some fashion. You might have noticed that I put a link there that said, not a link, but a notice that says, yeah, pretty much 100% of the students who were in class yesterday said, you know what, it's fine to just watch the videotape, and y'all had other things that you would better be able to do with the time. And so it's like very few people showing up in a classroom. That's fine. I'll do what I'm going to do. And if you're happy with the other resources, that's good by me. And so I guess you're going to be watching, if you haven't already, something on the partial F test. There was a lab on the partial F test that was due just a little bit ago. And there are homework questions related to the partial F test that were assigned. So let's get into week 4AB. The homework questions that are this week, darn it, this other thing's getting in the way. There we go. The homework questions are basically stuff out of the textbook: sheep, bird song, soybeans, cotyledons, lizards. And if you click your way into that, there is a partial F test question in the well as well, in the context of discussing an interaction. Okay, so a little bit of review on the interactions, and this is homework that's due tomorrow by midnight. So it's a good way to review for the exam as well. Okay, so any questions on the topics, partial F test and interactions, before we continue on with where we're at? Okay, so what I'd love to do, and maybe I should make sure I've got my blank PDF because I sometimes want to write on things. Okay, maybe I'll do it this other way. Mhm. Okay, and yeah, the name and somewhere on the Macintosh. Yeah, there we go. So then content. There we go. And that's at the very end of class today. Let's go back to our general linear model assumptions. We've been since week one when we talked about the t-test and you said you either need a large sample size or normal populations you're sampling from. And when we talked about ANOVA, we said we need the same standard deviation in each of the populations that you're sampling from, and you need a normal curve. Um, so we need that all. And we investigated that with residuals. And in regression, we talked about the regression assumptions of independence, homogeneity of variance, etc. And we said we could, again, check those with the residuals. Today, we're doing the same thing, but in this general linear model context. And I think what it really boils down to is we've got a method that works well in certain circumstances. Okay. And it works if the model that you're fitting matches the general linear model. Okay. Are these assumptions valid? Do we have really independence? Do we have the same spread regardless of the X values? Do we have normality in the errors around the trend? And do we have what we'll sometimes call linearity, like a lack of an interaction, a lack of a quadratic term, or maybe we'll call some of these things additivity, that literally we fit the right model that you don't need additional interactions. Okay. And so these are things that we're familiar with checking. So how do we go ahead and do those model checking? Well, maybe if we look at an example, that's going to be helpful. So let's go back to our friend, the income and life expectancy data. And that means I guess I need to find it. And where we go? Class exam. It looks like I'm even in the wrong class. 313. There we go. And summer 2026. And class examples, I for income. So that should be right there. And it's slowly indicating it's starting up GMP. One of the things that we've had you do in the labs in looking at the labs on Duncan's occupational prestige, right, when we sort of included the categorical variable as well as the quantitative variable, we're doing or we did what we're going to be emphasizing in class today. And again, a familiar example is one we can work with quite nicely. But if you believed the income is a predictor and life expectancy is the response variable, and you're fitting a regression model, or if you will, a scatter plot, draw a straight line through it. And I'm going to go ahead and do that. Income down here along the x-axis, life expectancy along the y-axis. And if I were to fit a trend line, a straight trend line, maybe if I were to drag type over here as a color, you can see it looks as though we have two distinct groups. There's the blues that are up high, and the bulk of them are above the trend line, and the reds that are down low. And again, the bulk of them are below the one trend line that we fit in. If you include only a quantitative X variable of income to predict life expectancy and fit a slope, it does look as though the errors around the trend line have some problems. Okay. Even so, let's go ahead and proceed as though that was a wise thing to do. Life expectancy, I could predict it based on income. Click OK. Yeah, run that. And one thing that we now maybe could do is within our model, I'm going to choose to save the residuals. Okay. We've done this before. We've saved the residuals. Essentially, we've got this new column that says if I were predicting life expectancy of a country based on only the income and fitting a straight line trend, the life expectancy I would have predicted is in this case 2.99 units too high. If I were to graph now these residuals against my X variable, my income, again, maybe if you're going to have a trend line, make it straight as possible. And let's not emphasize one particular row. Let's emphasize all of them. And I want to go with country type again with color. And this is not surprising, but I'm looking to see two individual problems. Looking to see two individual things. One of them is the blue group seems to have a bit of a slope. And if residual is what we couldn't explain, and if what we couldn't explain seems to be related to income, in other words, if I asked you, can you predict the blue dot? There's a blue dot that I'm gonna give you, and I'll tell you the X value is about 1,000. You'd say, trend line drawn in. Oh, I would expect maybe about a 10 or 15. And if I said my X value were about 5,000, you'd say the blue dot is likely going to be negative and maybe even -5, -4, -3, somewhere in that range there. There is definitely a trend here in the blue dots. In the red, also, maybe it's a little bit harder to see, but I see a bit of a negative trend line there as well. We maybe, instead of just the color, right, as the type compared to 1, 0 flat, okay, trend. Maybe we could even say, what if I fit a trend line in each group separately? And this is causing some of you to say, yeah, I remember this in chapters 6 and 7. If there is a trend line, okay, where group OPEC versus industrial, it basically tells me whether it's positive, like the blues, or negative, like the reds, that group is something that should have been incorporated into the model. And indeed, this graph shouts out at me, we need to have grouping information. Red versus blue, there's a noticeable negative residual for the reds, and blue, it's tending to be positive. If you can ever predict the residual based on which group you're in, that's a lack of independence. These are not data that are independent. If I tell you that it's an OPEC country, you're thinking the residual will be negative. If I tell you it's an industrialized country, you're thinking the residual's likely to be positive. If ever telling me that the residual's likely to be in one range negative or another range positive, you're telling me that's a group variable that could have been incorporated into our analysis. So let me go ahead and redo this model, recall what we had just done, and let's put country type there as well. I click run. I see okay, okay. Yes, I'm going to now I'm going to save, if you will, the residuals. Those save columns, those residuals. Yeah. A new set of residuals, if you will. I'm sorry. Darn it. I want to save the residuals. So save the columns and save the residual. This is my second set of residuals. So it gives a residual life expectancy 2, not the first one, but the second one. So versus the second model that I fit, how well am I doing now? Again, with Graph Builder, I'm going to say, well, how do we now do it predicting the residuals? And I'm going to drag again income along the x-axis because we know our x variable was income. And I like the lines to be straight, so I'm going to make them straight. And I'm going to put country type over here as an overlay because indeed, as an overlay, we see two lines drawn in to potentially predict the residual value based on X, the income. And here I'd see, well, typically the blue group on average are about 0. So the residuals are typically about 0. And I don't really see a steep slope. No interaction necessary. And with the red, I also see not really a steep slope. Again, no interaction appears to be necessary. So I'd be happy. Now, we seem to have a lack of independence. We've solved that. The former dependence, positive residuals for blue, negative for red. we don't have anymore. There is no longer a lack of independence because we put the grouping information into our analysis. So that's a thumbs up. Yay. I do still see a problem though, and you might be glancing at it as well. Do you see a vertical spread that's quite large in the reds, but small in the blues? I certainly do. Okay, so getting back into it, if we have missing information about country type, we're going to sort of have a bit of a problem. The independent, if you will, heterogeneous data. And the solution is to look in the residuals. And if the residuals say, aha, one group is different from another, systematically, sometimes the residuals are positive, but in other distinct situations, they're negative. Put into your model something that will allow the model to say, aha, this is the group that you're in. You have this new factor, industrialized versus OPEC. Can solve the problem. Another thing that we need, maybe let's let's jump right to here. Equality of spread, because we're looking here when we suggested earlier a lack of equality of spread. Red spread large, blue spread small. How do I get a now equality of spread? How do I even check to see whether there is equality of spread? Well, the nice thing is our residuals, our most recent residuals that we feel better about because our model had a categorical factor, country type, and a quantitative factor, sort of income. So those two factor, or I guess quantitative variable income, those two variables alone should predict life expectancy, and the residuals are what is lacking. If I were to try to compare those, we know that the Levine procedure for a categorical explanatory variable can tell me if the residuals are different across the categories. So where do we find Levine? Levine is, you know what? It's interesting that JMP hides various tools in places where it thinks you're typically going to want to use them. Here's a situation where I'm thinking I want to use the Levine procedure, and the only place JMP builds in Levine in an easy fashion is under analyze fit y by x. And that feels uncomfortable because we already did an analysis. We already did a fit model, but I'm going to use fit y by x for just the residuals. Do the residuals have a different are they different on average across the types? That's really, and the answer should be no. But remember, we have under our procedure the unequal variances. We could check for whether the variances are equal or not. And Levine is a way of checking that, and our Levine procedure has a p-value of 0.0081. It says the one group has a much wider spread than the other one. The standard deviation shown here for the OPEC countries is quite large, like 8. And for the other countries, the industrialized countries, quite small, like 1. We said at the beginning of the term, if you ever have a situation where the largest standard deviation divided by the smallest standard deviation is more than 2, you should maybe worry. Here, our ratio of largest to smallest is, my gosh, a lot more than even 4. And so I'm thinking here, we should not believe equality of spread. Does this mean we're out in a hopeless situation where we can't solve the problem? Not necessarily. I just want to say we could use Levine to check for equality of spread. In the same way that when we looked at our graph with Graph Builder, I said there appears to be a lack of equality of spread. Let's redo that graph. Maybe we have it. No, let's just redo it because that's easier. Those most recent residuals when plotted against the incomes right there. And then I'm going to make it straight and then grab type and make that an overlay. Although I wouldn't say this is funnel shaped. Okay, you almost are maybe looking at a funnel. That's by accident. What I'm really looking at here is vertical spread for reds, large, versus blues, small. Levine is the easiest way to check it, but you could also look graphically in the residuals plotted against your X variable, as long as you have group as an overlay or a color. Any questions about equality of spread or whether the residuals on average have a value of 0 or not? Okay. We also required things to be normal. Normality was the thing we needed. We needed the normality, or else we had said, there's not much we can do with our procedure. I guess, like before, you could always, with the data, say, do we have normality? Let's review how to get that. We believe our most recent residuals are better, even though there may be a lack of equality of spread. I'm still going to be checking for normality in those residuals. Analyze the distribution of what? Of the residuals that correspond to the model you think is best or most reasonable. I click OK. I like to have that horizontally aligned. And to check for normality, there's a couple different ways. That normal quantile plot, basically we're looking for a straight line, and I'm thinking that's sort of straight there, but these guys are not on the straight line, and neither is this one. It looks as though pretty much this middling region between about -5 and 5, we might have perfect normality, really straight, but we have these data stretched out further to the left than normality in the middle would suggest, and further to the right than normality in the middle would suggest. I could indeed add a continuous normal fit. Off to the left, it looks like, yeah, it doesn't fit my histogram very well. And off to the right, if we tried our goodness of fit, the Shapiro-Wilk procedure basically says, yeah, there is no way that you'd want to believe normality. If the population we're sampling from were in fact normal, we should never see a normal quantile plot with this curvature in it. We should never see this many outliers so far away from that central value. The normality that fits the bulk of the data in the middle doesn't fit things out in those extremes. So normality, I don't believe it. Does that mean this is a horrible example? Well, it means that it's an example where probably I wouldn't want to test or use the p-values to reach a conclusion. Yeah, we really would not want to use the p-values here because we have a lack of normality and a lack of equality of spread. Okay, let's go back and talk about one other thing that is sort of important, and this relates to, I believe, chapter 8. Pretty much anytime you do an experiment, okay, collect observations on an individual, your response variable needs to be one number per individual that you measured, or one number per individual that you treated differently. Okay. There was an experiment that I was involved in with some folks in soil science many years ago. And what we really wanted to do was to look at the amount of sediment in the runoff from artificial rain when we rained on these boxes of soil, and with different ways of planting. Caltrans really basically cares. If it plant a hillside with little seeds and the seeds grow up, and they keep then, I guess, the hillside above the roadway, or maybe the hillside below the roadway from eroding. Okay, that's the goal, is to keep the hillside from eroding. And the best way to do it is to have plants. There's a couple ways that happens. One is the leaves themselves absorb the blow of the raindrop, and the raindrop doesn't knock anything loose. Okay, one. Two, the roots provide some stability for the soil a little bit down underneath the level of the ground. And so what we're really looking for is how much the way we treat the planting of plants. I mean, which plants do we literally put in those boxes of soil, and then we rain on them in an identical way, artificial rain again. We measured the amount of runoff, and we had essentially 18 separate soil boxes, right? And we have multiple sort of information from each box, but each box itself is treated one way, and there's 6 different ways of treating the box. boxes. There was bare ground, and there was planting method A, planting method B, planting 5 different planting methods. And we have 3 replicates. In other words, 1, 2, 3 soil boxes had bare ground. 1, 2, 3 soil boxes had planting method 3. 1, 2, 3 soil boxes had planting method 5. And we rained on these boxes 1, 2, 3, 4 separate times right before the plants grew, and then at 1 month, 2 months, and then 3 months. You'd think that's a lot of data. You'd think maybe you have like 18 separate boxes, 4 rainfall events, 72 data points. In fact, we don't. We don't. Each box will provide exactly 1 data point. That's it, 1 data point per box, period. No more, no less. Moving over here off to the side to make an aside comment. In another stat class, which you can sign up for in semesters, it's not called Stat 419, but it'll be called something else. Literally, we can handle situations where you have multiple readings per treatment unit, per individual box. We'll show you a way of tackling that. And in a different class that we are going to be offering, I think it's Stat 3530 or 3540, we'll talk about another method that our book it's in, okay, in random effects. And I don't want to go into it because it's the summer term and we want to get the summer term done in the summer term way, which is at an accelerated pace. And so, oh well, we're not going to cover it this term, but you could sign up for the follow-up class later on. So there you go. There are some things that you could look for. Basically, you get 1 data point per individual unit that you treated. And if you don't, then there's a problem. Okay. Let's yeah, okay, so moving on. And then let's get into the last thing here, and that is a solution when we have a lack of equality of spread or a lack of normality. Here are ways that we could fix the problem. And let's make it bigger. This is also in the lab, but make it big enough that we could see here. You can check for those 1, 2, 3 things pretty easily. One is, are the residuals skewed or not? Second thing is the average of the residual 0 for every rational little subgroup that you look at? And is the spread equal or is it unequal? Okay. And so you're thinking normal or not. If it's not normal, the question is it skewed? And if I'll tell you, you have the results of the residuals aren't skewed, but they're normal in shape. Okay. And if I furthermore tell you the residuals are always with an average of about 0, and the spread doesn't lack equality, you're happy. We've got a model which is sufficient. We could use it. We could trust the p-values. We could use confidence intervals with confidence. Okay. All's right with the world. Okay. However, here's another common situation where you've got skewness, okay, and you've got the residuals being unequal in spread, okay? And so what could you maybe do? Let's transform the response variable. That's a suggestion. I'm not telling you these are the surefire things that will solve all problems, but they will start to solve some problems. Usually transforming an explanatory variable or adding a polynomial term, or transforming an explanatory variable, or adding an interaction. These are things that statisticians over many years develop some intuition about the correct, if you will, solution to any particular problem. Okay. So hey, that's fun. My little green arrow is still on the screen no matter what I do. Okay, so we'll roll with it. Last page. We're suggest, okay, if the result is you should transform Y, okay, we're saying, hey, ideally, there is a number out there that we would love to be able to know what it is, what is the best value for lambda, if you will. We should raise Y to a power of lambda, if you will, a new y variable might be a great way to go. This is why we sometimes will say things like, oh, take a square root of the response variable and then refit. Or perhaps take a log, a natural log or a log base 10 of your y variable and then refit as though that is the proper value for lambda. We're saying in some situations, all we need to do is to find the best lambda, the best power of y to fix the equality of spread problem. Okay. It will also often fix a lack of normalness. Finding the ideal spread, okay, maybe matches up to finding the ideal transformation to fix the lack of normality. And so we're going to say that's done with what we'll call the Box-Cox transformation. That's a tool that's built into GMP. And ultimately, what I like to do is rather than emphasize Box-Cox as a method, I'm going to say, let's talk about power transformations. They're really the same thing. This formally is a power transformation, lambda raised to the power, or wide raised to the power of lambda. Yeah, we're home free. And then I guess in a technical sense, if lambda is 0, we're going to use which is the natural log of y. Okay. Y prime is the natural log of y if lambda is 0. It's a way of saying, oh yeah, just find the best power of y, lambda. Okay. And how do you identify that? Well, I'm going to try in the context of a data set that we've looked at before, or maybe a different one. Let's go with a catfish for now. I don't know. No, I can't use that for this data set. Hmm. Okay, so let's go with antibiotics. You all looked at those recently in the context of one of the homework studies. So we get the different binding percentages as a function of which antibiotic it is. This is not a general linear model, but this is just a straight ANOVA. But if I were fitting a general linear model, it's under fit model, okay? And the binding percentage y may depend on your x variable or variables. You click run. Now, I'm not wanting to focus on all of the things here. I want to focus in on just how to use the Box-Cox transformation approach. Okay, so how do I get that? I have to apparently move this thing first, the Zoom little guidance thing. So, uh, yeah, the things that we don't know, what do we do with them? Let's try. Yeah, no, none of these say Box-Cox. Estimates, no, none of those say Box-Cox. FX screen, no, not really. Factor profiling, hold on. Box-Cox transformation. So, like where we saw profiler, right? Or interaction plots, we see the Box-Cox transformation. So if ever you're saying, I don't know that I have what I need in terms of the best way of expressing my response variable y, try this Box-Cox transformation. With this Box-Cox transformation, let's pull this up higher so we could see it. What we have here is a graph that shows us, and I don't want to get into it, this more of a question for stat 3540. Okay. I'm just saying there is identified as a best lambda. The minimum lambda is shown here as a function. I guess it is us this SSE. The lowest SSE is, if you will, best. Okay. And so my lambda, okay, that's optimal is right here at 0.663. In other words, what we're saying is the best model out there would be for y to the power 0.663. And that's sort of awkward because y to the power of 1/2, that's a square root. Y to the power of 1, that's don't transform y at all. Y to the power of 0, like we suggested, that's just a natural log transformation. This is the range where our blue line here is below this red horizontal line. And again, our stat 3540 class, if you wanted to take that later on, will show us more details. I'm just saying let's zoom in until we can see which exact blue line values are below red and which are not below red. And that's where I'm thinking any lambda in the range about there, which is, well, 0.1 to about here, 1.4. Anything in the lambda of zero point 0.1 to 1.4 range is as good as, or not significantly worse than, the best lambda of 0.663. So that tells me a lambda of 1 is acceptable. A lambda of 1 is no transformation whatsoever. A lambda of 1/2, also pretty darn good. That's a square root transformation. No problem with either a square root transformation or a no transformation at all situation. Okay. So box Cox will show you the range of plausible values for lambda. And as long as you choose one that seems optimal or better than that, close to something that is typically used in real life. Like sometimes naturally you'll square things, sometimes you'll naturally take a root, sometimes you'll naturally take a log. Sometimes it's 1 over the square root of something, or sometimes it's just 1 over the value of something. The natural way to go. But the claim is across lambdas in the range, say -2 to +2, one of the lambdas, y to the power of that optimal lambda, will be best. Choosing again something inside the box Cox range of acceptability, in this case 0.1 to 1.4, is going to be as good as optimal. Optimal is 0.663. I would go with 1 in this case because it's the easiest to interpret. No one wants to ever look at the square root of binding percentage is different on average across my different groups, my different antibiotics. I'd rather say the binding percentage itself is different across the antibiotics. So that seems to be what I had in mind for you to see in class today. Again, remember two things. One of them is, yeah, there's this test coming up. Two, in class tomorrow, what I want to do is to spend time in going over the sample exam as much time as you want, or any topics as much as you want before you take the actual test. The topics that are most likely going to be of super great interest will be interactions, and in particular, categorical interactions, or quantitative interactions, or perhaps the partial F test, which is not hard, but it's hard to get it down. And so I always recommend having a note sheet in front of you while you take the test, because if you have something to refer to, then you're in good shape. So that's where I'm going to stop, unless any of you has questions, in which case we'll dwell on your questions as long as you like. Any questions? Okay.
I think I'm good. Thank you.
Yeah. So I'm going to stop the share then, and I'm going to stop the recording, and